All right, let's look at logs and exponentials as inverses, and we'll also look at some characteristics of the graphs of logarithms. We talked about finding the inverse in chapter 1, and we just switch the x and the y and then solve for y. So today we're going to do that with logs and exponentials. So we'll rewrite it with a y, switch the x and the y, solve for y, and we can cancel the e by doing natural log of both sides. And what's happening here is ln can be written as log base e. So we really have log base e of e to the y. To what power do you raise e to get e to the y? You raise it to the y power. So then we can say the inverse is natural log of x minus 1. Rewrite it with a y, switch the x and the y. And then we will cancel the log by doing base e on both sides, exponentiating base e. So e to the x equals y plus 1. E to the x minus 1 equals y. The inverse of f is e to the x minus 1. And if we don't have base e, we can always do whatever base is given. So if we have y equals log of x, that means y equals log base 10, and we'll switch the x and the y and solve for y by exponentiating with the base 10. So 10 to the x equals y. Same thing here. So here's the function, and we switch the x and y. and now get y by itself. We'll have to divide by 3. And we don't want the log there, so we'll exponentiate. This is base 10, so we'll go 10 to the x over 3, 10 to the log, 10 to the x over 3 is 0.5y, and we'll just divide by 0.5. There's the inverse. Okay, try that one. Pause and try that. Divide by -2. We want to cancel this natural log, so we'll exponentiate with base e. And then we'll get y by itself. Find the inverse of that. Pause. Switch the x and the y. And we want to get y by itself. Divide by 3. We don't want e. We don't want 2. Let's get rid of the e first. And that will be with natural log. Divide by 2. Pause and find the inverse. We want the y by itself. We don't want the 1, we don't want the 10, but we're going to do the inverse of this exponential first. Let's do log of both sides, or log base 10. Here we have a base 10, so we'll do log base 10 of both sides. And if we have the 10 there, this says, to what power do you raise 10 to get 10 to this power? You raise it to this power. So that's how all that cancels. And when you write this, be careful that you don't read it as x plus 1 in parentheses. If you had to put parentheses, they would go like that. Okay, and then there's another type of question on graphing in the book. So this is just a review of logarithmic graphs and also this notation. So let's draw the graph. Just draw what's given. And we know at At 1, the y value is 0, so we get that point. We know the shape of logarithmic graphs. The parent functions go like that, and exponentials go like that. Logarithmic graphs have a vertical asymptote, exponentials have a horizontal asymptote. So this must have a vertical asymptote. And now we have to pay attention to this. As we go to 0, the limit is negative infinity. As we go to the right, the limit is infinity. So this shows the y value is going to infinity as we go to the right. And then as we go to 0, the y value is going to negative infinity. And let's look at the y-intercept. There's no y-intercept because there's an asymptote. The x-intercept, I'm going to say that this really says going to 0 from both sides, we have this. So I think it's a little unclear because we could have a logarithmic graph that goes like this if we just squared it. Let's just stick with this. Domain. The domain, all the x values that have a point on the graph, so the x values start at 0 but not including 0, so we go to infinity. Not including 0. Range. Go all the way down to negative infinity and all the way up to positive infinity. The range negative infinity to positive infinity. Symmetry. Symmetry from chapter 1 was, can you change the x values and still get the same y value? Can you change the y value, the signs on the x and y values? And there's no symmetry here. We also can't draw a line of symmetry anywhere here, so there's no symmetry. And if we just say it's continuous on its domain, then we can say it's continuous from 0 to infinity. Is it increasing? Yes, this arrow does not mean decreasing. We don't read it as decreasing. We read the graph from left to right. And so it's increasing from 0 to infinity. And then when is it decreasing? It's never decreasing. Okay, same question. And try that one. Pause. Here we have a -1, we go to 0. As x goes to the left, we go up. As x goes to 0, we go down. And that is, there's a vertical asymptote. The y-intercept, none. X-intercept is -1. Domain goes from negative infinity to 0. The range goes from negative infinity to positive infinity. Symmetry, none. Continuous on negative infinity to 0. and increasing never, decreasing from negative infinity to 0. So increasing, this doesn't mean increasing. We read it from left to right, so it's decreasing. It's not increasing, it is only decreasing. All right, there's the parent function, and then we're given a graph of g, and we have to figure out the equation for g. So g has this point and this point. And that's what the question looks like. So we can do this. This you can also see. You see that it gets shifted up to. If it's a little more complicated than that, if you go point by point, it's a little safer. So let's write down the coordinates 3, 1, and then we'll write down the coordinates and figure out what the function will be. So here we're going to go 1, 2, and over here is 3, 3. And then we look, the x value is not changing, and we went plus 2, plus 2. It worked on both of them, so it looks like the function is going to be adding to the y. We're adding to the y. That's a vertical change, so it must be outside. And we would say that g of x is log base 3 of x plus 2. So there's f of x, again, the same function, and then we'll go g of x. Okay, try making the same table. Pause the video. So I wrote down the transformed points and the parent function points. We can see what's changing. Looks like we have a plus 2 on the x. So if we have x plus 2, that's horizontal. That's an inside change, and we have to remember to do the inverse. So it would be log base 3 x. We added 2, so we have to do the inverse for the inside. That would be the transformation. And now we'll go with log base 2, so that'll have a parent function with a point here, and I'll go over 2 up 1. All right, and then g of x is going to be over 2 down 2. Let's do another one. Same parent function. And then we have points at -1, 3 and -2, 2. Okay, so find g of x for each of those. Pause the video. All right, that point is the same, and then this point is 2, -2. So now we have to look at what happened. When we see this, maybe we'll say -3 on the y, but it didn't happen over here. So this turns out to be a dilation where we're multiplying the y value, because when we multiply anything times 0, we still have 0, but over here we must have multiplied by -2. So that's a vertical change. That's outside, so we know it's just going to be like that. And we'll have g of x is -2 log base 2 of x. Okay. And we have to write down the points of g. So that's -2, 2 and -1, 3. And what happened here? We may have done a -3 and -3. Well, that works. +2, +2. So that works. The -3 is horizontal, so we know that's going to be inside. And if we do -3, we have to do the inverse there. So we're at log base 2. There's our horizontal change, and then +2 outside. All right, and that's it for today.